Philippa says, some of us have been doing this for the last 3 and a bit weeks, and we're tired now. So this is the second of 2 workshops, and in between we've done little bits of actual work, which was great. The first one was sort of a slightly more inward focused technical thing, big specification proof and testing at scale, for which there will be any number of slides and videos and things online. And this whole enchilada is organised with Philippa and Neil Krishnaswamy, who couldn't be here today, and Shankar. So I thought I would kind of reflect a bit. So we heard in the first 3 weeks kind of an interesting bunch of success stories, maybe some non-success stories too, but an interesting bunch of success stories. And I thought I would reflect a little bit on some of those and hopefully not, misstate them too badly, and maybe draw out some lessons about failures and risks and enablers and adoption paths, not for formal verification per se, but more strictly for big specification. And I'll talk about that. So let me step all the way back to the foundations of computing. How does it work? Well, we go to Amazon and we look for good books. This is one of the classics of the subject. How many of you knew this book when you were young? Not a very UK-centric audience here. Philippa knew the book. Andy Gordon knew the book. It's a great book. Apparently the Ministry of Defence tried to buy a bunch of copies in brown paper covers to give to its staff because they were embarrassed at reading a children's book. It is a great book. Also great is the classification that Amazon give it, which I think is entirely correct. Because the problem of building computer systems is a sociological one, right? Because these things, if we look at the big picture, I have to say on my laptop that was a nice warm gold colour. But if we look at the big picture, then they are far too big and complicated for us to understand. So computing is subdivision and abstraction, right? We divide these into software and hardware, and then we divide the software into compilers and operating systems and stuff, and then we divide the compilers into different compilers and pieces of compilers, and then we keep on doing that. And if only my LaTeX was good enough, I would have drawn an animation of a decreasing fractal, but life is too short. Right? So we keep on dividing things, and that is essential for them to be small enough for us to understand, but we abstract things even more crucially so that we can build this layer without understanding that layer, and build that layer without very much understanding that layer, and so on. And obviously, this is a cartoon, and it's a gross oversimplification. These things do not exist in real layers, but still, roughly, it's like that. So this is a deeply misleading picture, right? Because if subdivision and abstraction are our daily business, then the little lines in between the boxes are what really matter. Right? So that's what I want to draw attention to, as I often do. We have, architecture specifications that tell supposedly the compiler and operating system writers what they can depend on, and tell the hardware developers what they have to implement. And this, let's say for ARM, last time I looked was a 14,777 page PDF. Right? So that is not a tiny abstraction, and it's a bit tricky to work with, but compared to the size of a processor implementation, it is tiny. So there is effective massive abstraction going on, and the same at each of these other layers. Right? We mostly, in this room, mostly don't have to understand all of those things, and a good thing too, and so on further up. So, in the dawn of time, that was quite easy to arrange. So here is the EDSAC, which was one of the 3 first computers, and that's, the machine with Maurice Wilkes, who led the project, and lots of valves. And it was very complicated, filled a room, as you can see. but it could be abstracted quite effectively into the specification of its instruction set, which fits on one page in the book. And it's beautiful. It's probably a bit tiny to read at the back, but here the instructions are numbered A through Z, and A is add the number in storage location N into the accumulator. So that is not a totally formal spec, but it's pretty close. If someone told you how many bits are in the accumulator, there would be no ambiguity there. And then it runs through to Z, stop the machine and ring the warning bell, which I mourn the loss of over the years. So that was a sort of straightforward and good abstraction that you could achieve in about 1959 or something. So then, skipping ahead to 1976, Dijkstra, famously optimistic guy, wrote this, that he could remember this golden age. I don't know if he probably wasn't talking about the EDSAC, but he could remember the time at which interfaces were achieved with a clarity that satisfied everybody's needs. And this rigorous and indispensable clarity did not only extend itself over the hardware, but also over the basic software. Sounds good. 1976, and it's all got better since then. Yes? Well, you can sense from his tone that there is a but coming up, and it's a great but. Properly bracketed, obviously. Sad remark. Since then, we have witnessed the proliferation of baroque, ill-defined, and therefore unstable software systems. Instead of working with a formal tool which their task requires, no subtext here, many programmers now live in a limbo of folklore, in a vague and slippery world in which they're never quite sure what the system will do to their programs. Under such regretful circumstances, the whole notion of a correct program, let alone a program that has been proved to be correct, becomes void. And what this proliferation of such systems has done to the morale of the computing community is more than I can describe. Well, if only, I say, because the computing community seems to have done okay since then. I mean, many of them are, financially set, and large companies have existed, and we have phones in our pockets that do miraculous amounts of computation. But we have, I think everyone here would agree, seen, as it were, a bifurcation of paths since 1976, in which mainstream engineering has gone off and done pro-specs and test and debug development, and that has worked to create an industry, but clearly built things which are hopelessly insecure and impossible to engineer decently. Meanwhile, another community has gone off down the path of trying to understand these things more rigorously in many different ways, usually, but not always, with a focus on full verification and proof. And on the whole, in the 50 years since then, there have been some great point successes, but it has remained niche. Right? So the case I want to put, based on these examples that I'm going to quote in a few minutes from the last 3 weeks, is that there is an actual possibility of convergence visible in the not too distant future, maybe, if we're lucky, and a bit creative about it. So, if we go back to this picture, some successes. We heard, so sorry for those of you that have been here for the last 3 weeks, because some of this will be repetitive, but we heard down in the microarchitecture level, Anna Slobodova at Intel talking about a totally successful project doing micro-operation specification and hardware verification for an in-progress major Intel design. They made great friends with the design team. After a little while, some model checking people came along and said, "Oh, would you like to use our model checker?" And the design team said, "No, thank you, we don't. We have Anna." Amazing win. At the architecture level, so a few years ago, Alistair Reed sort of dragged ARM, not exactly kicking and screaming, but certainly with some kicking, from a world in which their sequential instruction set specification was written in pseudocode, in Word, basically, into a not exactly formal, but mechanized language that could be tested against. And the reason that he could succeed in doing that was not because the architecture designers wanted it, but because the hardware verification engineers, where verification mostly means testing and some model checking, really wanted a spec that they could test against. Alistair is now in Intel and trying to do the same thing in Intel. It's like a one-man hero of the industry. So Robert talked a tiny bit about Cherry this morning. In the Cherry project, initially an academic thing, now also an industrial thing, we managed to get an amazing virtuous circle working in which the designers used formal specs of the instruction set, again the sequential behavior of the instruction set, as their primary design tool, and used that as a test oracle for testing against, and a thing to generate tests from, and a thing that is directly included in the documentation. And we did that partly because we were just feeling virtuous, and because I wanted to experiment on my systems colleagues. I think Robert has left now. It was a great experiment because they bought it. Right? They adopted it as their very own. And they did this because building a new architecture and FPGA processor implementations and a software stack and all the tooling and all of that is quite a big task for a little academic group, even a big academic group. And doing this made it easier. It was not a cost, it was a benefit. And we're trying to get the RISC-V people to do the same. They sort of buy into it. Some of them buy into it. Some of them find it all a bit weird. Moving up. Nuno Lopez has worked for the last several years with a bunch of other smart people to looking at the intermediate language of the Clang LLVM compiler stack. They have effectively written a semantics for that intermediate language in the form of a great big pile of C++, which symbolically model checks candidate peephole optimizations. And this is now routinely used by LLVM developers. They say, is this a bug? We'll ask alive2. I'm submitting a pull request. I will include the alive2 link to whether this is a correct optimization or not. Right? They do it routinely. They don't look at the semantics. They don't read the semantics, but they use that tool. It therefore now is the semantics of LLVM in a substantial way. Other people have mentioned earlier, WebAssembly, so Andreas Rosberg and Conrad Watt and other PL people started the whole thing with a PL theory education because they were properly brought up individuals and have managed to maintain that. Right? So the whole language has an initially on paper and then mechanized in a prover and now being mechanized in other fancier ways, as Philippa mentioned, formal spec. On the programming language level, this is kind of a more nuanced story here, right? Because it is still, to my great distress and quite shockingly, the fact that basically no programming language ever has a precise and normative spec, despite the fact that PL people are the ones working on that kind of thing. No language that people use at scale by typing with their own fingers, in contrast with these two. So there certainly is a lot of formal work, embedded in the designs of these things. And there are, where is Gavin? Gavin? Oh, there's no more Gavin. So Gavin Bierman at Oracle and other people like Nick Benton and his fellows at Meta have been, behind the scenes fighting the good fight and gradually evolving languages which are quite disgusting closer to standard ML. They have. But these languages, likewise Ralph, who we'll hear from tomorrow for Rust, these languages are informed by PL theory, but they don't themselves have big specifications in exactly that form. But we certainly have successes in, well, again, not exactly in using the semantics directly, but in building analysis tools which are certainly based on some semantics to find bugs at scale, as Peter described. It's Peter, he's got the two.
We've picked 3 people with family.
If only we'd had a nice
and they apologise.
tight program. Let's see, so also, well, both at the architecture level and the programming language level, but in a particular technical niche, a bunch of people here and elsewhere have worked on the relaxed concurrency models of these things. And this is an interesting niche because it was totally clear way back when, in, I don't know, 2007 or something, to many key people in the industry that they had a problem in that they didn't know how to describe their architectural spec intentions or their programming language spec intentions, and a bit of semantics and test generation and testing and so on clearly solved problems, and thereby got take up. And it's now kind of routine for both at the architecture level and at the programming language level for people to feel embarrassed if they have not at least made a good go at trying to define the actual concurrency model that they have, or at least talk to someone who might. Popping up, so June talked about SEL4. In the last few weeks, we've heard about, I think, 3 or 4 other hypervisor verification projects, all of which have correctly perceived that this is a great niche, a high-value niche that justifies even quite costly things, although one would hope to make it less costly. Going up, Nate Foster. So many of you will have heard of software-defined networking, so languages for configuring SDN routers. But this P4 language is used for configuring SDN routers and also for modeling these configurations. And Nate described, work to nail down what that is, along with a bunch of other cool stuff. I failed to get onto the slide, quite ironically, because of an apparent LaTeX bug. Kind of vaguely related work by Nick Swamy et al. With their F-star system, which is a fancy dependent typed programming language with an extraction story, using which they have managed to get something like 1 million lines of verified code deployed into large-scale production in particular niches, right? Particular crypto niches and parsing of incoming packets and such like. And we had, so now this going back into sort of full verification, Sandrine Blasi spoke about the fact that ComCert is now, which you all know of and has been developed for many years, now has some honest-to-goodness certification for use in some of the Airbus applications that they've targeted for so long. And so that's fighting the social challenge of dealing with regulators. So this is kind of great. It's not what we would have expected 10 years ago. All the way up and down the stack, we have success stories. So we can go and get a nice cup of tea and go home and get an early night, and life will be good. The rest of the industry will just look at that and say, oh, yeah, we should do that. We'll all do that. The whole Rust community says that, yeah?
Sure.
So all of those are kind of successful. Why are they successful? So now, this is me casually reinterpreting things that all those people have said and teach a bit of my experience too. Each of these is in a pretty different technical and social context. And there are some common themes and there are some interesting differences. So many of them are supporting and extending conventional engineering one way or another, right? Rather than saying, yeah, we'll do it our way and you just use the result. So the F-star and the ComCert things, I guess, are more in the replace it domain. Most of the others are supporting and extending conventional stuff, right? And the key way, in many cases, is to make specifications which are not Word documents, but things which are executable as test oracles. I don't by that mean things which are executable in the conventional sense, but specifications for which one has some way of deciding the question of whether some observed behavior is allowed by the spec or not. Right? That's the property you need for a spec to actually be something you can compare against implementations, right? And the world does test and debug development. If you can't test, the specification is basically meaningless. Several of them use the specs as primary documentation, and that requires that they be written in a form that is acceptable to the audience. Some of them, like this Cherry case, ARM ASL from Morello, probably a bunch of others, use the specs as a primary design tool. Some of them are coming along after the fact, clarifying some existing abstraction. And that is a huge deal, because I'll come back to this in a minute, but the amount of technical debt of, the kind of stuff that Dijkstra was talking about, the vagueness and confusion that has accumulated since 1976 is quite mind-boggling and deeply scary. So that is a big deal. But in other cases, the same techniques, after one has become, good and strong by doing that kind of thing, can be used at design time and are used at design time. And then sometimes there's proofs of specification properties. So we proved some facts about the Morello ISA specification, for example, that found that it needed to be fixed. And just occasionally there are proofs of actual honest-to-goodness implementation correctness. But there is a huge amount of mileage to be got before one even tries these things. Although if one is aiming to try these things, one needs specs that you can believe in, and specs that you can believe in basically only arise by long iteration doing these things. Another big theme, the interplay between specification and testing and analysis and verification is like totally key to most of these successes one way or another. Right? So very old school formal methods was sort of proof or nothing. And there are many sort of more constructive interactions that one can get. Let's see. So these boxes are a lot smaller than these boxes. They change less often. They're more pervasive. There are also, of course, within some particular product, there are boxes of both kinds. But the interfaces are really a good target to leverage to improve engineering. Fixing the specs of ARM and C and whatever are by no means automatically going to solve all the problems in the world, but compared to other places where one can put one's effort, they're pretty high value. I said I would talk about failures. Let me talk about some failures. Got some instructive failures, not total failures. So in C, there's basically, in some sense, it's bankrupt. Right? The level of technical debt is no longer payable in a particular way, right? A particular sense. So quite a lot of the C standard is written in a weird and complicated way, but when you really pay attention, it does say something unambiguous and you can make some sense of it. But some aspects of it, like some aspects of the memory object model and what integer pointer casts you're allowed to do, and what the semantics of reading uninitialized variables are, and what's the, do subobjects really exist, or are they just an illusion? So questions like that have a wide range of different answers, and if you ask different expert C programmers, you will get different answers, and if you ask different parts of a single compiler, you will get different answers. So one of the shocking facts that came from Marion, who's probably here somewhere, and I learned over the last few years, is that one part of GCC assumes that the compiler can pay attention to the origin of a pointer value. The front and the middle end assumes that and optimizes on the basis of it. The back end, on the other hand, was written by other people at a different time, and it assumes that pointers are just numbers. So it makes some optimizations based on that. And some of those optimizations are not sound with respect to that, and vice versa. And this is not going to change, because these are really baked into those two quite large parts of that quite large compiler. So it's not really fixable. Not completely fixable. One can fix a bunch of aspects of it, but you can't really sort it out. I mentioned already, programming languages still basically lack normative precise definitions. I think there are technical reasons why that has been hard, but those I believe are totally surmountable these days, if only we had some good tooling, which we kind of know how to build. But socially, maybe not so much. This is a nice quote from Bacchus talking about Algol 60. The author had hoped to complete a formal description of the set of legal Algol programs, IAL actually, and of their meanings in time to present it here, he wrote in 1959. Only the description of legal programs has been completed, however. Therefore, the formal treatment of the semantics of legal programs will be included in the vaporware which we have sadly yet to produce. I and my colleagues had a nice project back in the early 2000s. This was one of our first exercises in sort of big-ish specification, looking at the TCP protocols and the sockets API to them. And we produced a fine spec that was experimentally validated and tested and written up and documented and annotated, and people could actually use it. People who didn't know the formal, any of the formal stuff could use it to answer subtle questions about TCP just by reading it. But, so it was a big success, but it was also a big failure because we made it executable as a test oracle, but in a way that was too fancy for practicing engineers to actually use. You had to have a theorem prover and drive it in a particular way and so on. And socially, we lacked the will and the resources to push it into the IETF community because, well, all the postdocs had worked for several years on it and they got other jobs and they left. Yeah. So that brings me to, I think this is my lastest slide, although it might take a few moments, to some risks and some enablers. Right? So if we look at these success stories, then each of them has been driven by a pretty small team, you know, 3 or 5 or 10 or something, of usually ace researchers and engineers working usually heroically, committing themselves to doing that for quite a few years. I think June said 9 years for the 9-person years for the first SEL4. Yeah? And this TCP spec thing, that was, I mean, all of that all put together, it was sort of the same scale. So that's really annoyingly long on the timescale of individual postdocs who have to, establish careers and things, and really inconveniently long on the standards of normal research funding. So in some cases, this is going on inside a company, and Byron talks about lots of great AWS stories where Amazon can commit to developing and maintaining those things. But a lot of these things are happening at sort of pan-industry interfaces, right? No one company has a vested interest in making C not be terrible, or LLVM, or even RISC-V. Right? There is a RISC-V umbrella organization, but it basically doesn't have a budget. Right? It has volunteers and committees. So we don't have really a mechanism to gather support from the people who actually benefit from this kind of work, right? Which is a big question, right? How can we organize and fund persistent work on what is really global infrastructure, but not as it were, a cost on everybody, but not in the budget of anybody. Robert tossed out some numbers for cost scale. So maybe it costs, I think he said about $1 billion to move something like, I forget if it was Windows or Android or both, from existing C, C++ to memory safe cherry C and C++. And that estimate is based crudely on what the cost was to port to 64-bit from 32-bit. We think this is maybe maybe a little less invasive, but sort of similarly invasive. Yeah? So on the global scale, that is a trivial cost. I mean, totally trivial, right? We should, as a society, be paying it, no question. Some of these things I've been talking about here, these are dirt cheap, you know. 10 million would get you, I don't know, it would get you a lot. 100 million would get you a huge amount. 100 million would get you, maintenance of all of those projects by all of those groups for the substantial future. But we don't have a way to sort of gather that at the moment. And then my last point is, there is an amazing community of formal methods and semantics people, but now all of them are employed by Byron to a pretty good approximation. And we don't really have ways, A, of replicating them, and B, much more widely, of educating the practicing engineers and the new students so that they would routinely use some of these more lightweight methods, even if they're not going to be theorem-proving experts, right? We don't have, well-established courses in places that are not, Imperial and Cambridge and whatever, where it just becomes second nature to the young students that they should be doing something a bit more rigorous, even if that is writing their specifications as assertions in C. C being, as many of you who will have talked to me in the last few weeks know, the best specification language in the world, because it needs no tooling whatsoever and no special education, except understanding that one is writing specifications, not implementations, which is really something we should be teaching the kids. With that, time is ticking along. I shall stop.